Now we can begin talking about intermolecular forces. If you think about it, there are two types of forces that act on molecules. The first are intramolecular or within the molecule forces, and we've discussed these before, only then we call them bonds. Then you can have forces that interact between molecules. Those are intermolecular forces. And we use the intermolecular forces to explain some physical properties of molecules. Now, intermolecular forces frequently are abbreviated IMF, and they are the attractive forces between molecules. As I said, these help explain several physical properties, most notably melting point and boiling point. And the reason we had to deal with bond and then molecular polarity is that molecular polarity will determine some of the intermolecular forces between molecules. Now, there are four types of IMF. The first are called London Dispersion Forces, or LDFs, and by the way, London is after a chemist named London, not the city. Something called dipole-dipole, hydrogen bonding, and ion dipole. And we're going to start by talking about London Dispersion Forces. Now, London Dispersion Forces occur between any two molecules, polar or nonpolar. But for nonpolar molecules, that's the only intermolecular force. And the size or the strength of the LDF depends totally on the size of the electron cloud. Now, in nonpolar compounds, electrons are shared equally. Here's an example of two compounds with the electron clouds around them. And we talk about electron density, and in this example, both of these compounds seem to have the same density. But that density is an average. Sometimes the electron may spend more time on one side of the cloud than the other, and so the density is not going to be uniform amongst all molecules. When that happens, as with this molecule, you can see that the right side of the molecule over here is a little bit darker blue than this side here, meaning that at this moment in time, the electrons are spending more time to the right. This is called an instantaneous dipole, and it is a vector. And it turns out instantaneous dipoles can be attracted to each other, negative to positive. The strength of an instantaneous dipole is related to the size of the electron cloud. The more electrons you have, the larger the electron cloud. The larger the electron cloud, the stronger the instantaneous dipole, and the stronger the London dispersion force. Now, the size of the electron cloud depends upon two things. The first is the molar mass. The larger the molar mass, the larger the electron cloud in general. This is because you either have more atoms or atoms with a higher atomic number. In both cases, you have more electrons. Or the surface area. The larger the surface area, the larger the electron cloud. It's spread out further. Take chlorine. It's got a molecular weight of 70.90 grams per mole. Compare it to bromine in the same group. Bromine, 159.8 grams per mole. Obviously, the bromine has the larger molecular weight, and we would say it should have the larger electron cloud. One of the ways to measure intermolecular forces is with boiling point. Chlorine has a boiling point of minus 35 degrees Celsius, whereas the boiling point for bromine is about 95 degrees higher. The higher the boiling point, the stronger the intermolecular forces, because it takes more energy to pull the molecules apart. How about surface area? Let's look at these two molecules. Now, both of these molecules have the molecular formula C5H12, so they both have a molecular weight of 72 grams per mole. The molecular weights are equal. Based upon what we just said, we would then expect the boiling points to be the same. When you take a look, the one on the left is called neopentane, and it has a boiling point just under 10 degrees Celsius, and the other one, N-pentane, has a boiling point that's approximately 4 times larger. But if you look at the red lines, which represent the surface area, you see the red line for the neopentane is smaller than the red line for the N-pentane. The larger the surface area, the greater the London dispersion force. Now, when you're asked a question and the answer involves London dispersion forces, if you're asked to explain it, you cannot stop with mentioning the mass or the surface area. you have to mention the size of the electron cloud and the fact that a larger electron cloud has a larger instantaneous dipole. So for the previous example, I would say the N-pentane has a larger surface area, which allows for a larger electron cloud, which allows for a larger instantaneous dipole, which means greater London dispersion forces, which means a higher boiling point. And that's London dispersion forces. Next, we're going to cover dipole-dipole. And this is an intermolecular force between polar molecules. And it occurs in addition to London dispersion forces. All intermolecular interactions involve London dispersion forces, but only polar molecules have dipole-dipole. So for example, take hydrogen and bromine, hydrogen bromide. Well, bromine is more electronegative than hydrogen, so it is polar. And you see that the bromine has a slight negative charge and the hydrogen a slight positive charge. If you put that in with a bunch of other hydrogen bromides, Coulomb's law says opposites attract, and so they will start to line up, negative bromine close to positive hydrogen, and there'll be an attraction between the two of them. That will pull them closer together and pull them tighter together. The dipole-dipole intermolecular force for hydrogen bromide is greater than the LDF, but both are present. But you may be asked which is the greater, so you have to say the dipole-dipole. For molecules of the same size, compounds that have the dipole-dipole forces, or the polar molecules, will have stronger intermolecular forces than the molecules with just London dispersion forces, and so things like boiling point and melting point should be higher for the former. So here we have two molecules, formaldehyde and ethane. Formaldehyde has a molecular weight of 30.03 grams per mole. Ethane, it's 30.07, essentially the same. This is a polar compound. This is a nonpolar compound. This has London dispersion forces. Ethane has London dispersion forces. Formaldehyde has dipole-dipole because it's polar. Ethane does not have dipole-dipole. The boiling point for formaldehyde is minus 19.5 degrees Celsius, which is low, but it's not as low as ethane at minus 88 degrees Celsius. Now, for molecules of different sizes, it is possible for the total London dispersion force of the larger molecule to be stronger than the combined London dispersion force dipole of the smaller molecule. Here we have ammonia and we have butane. The molecular weight of ammonia is 17. That for butane is 58. This is polar. This is nonpolar. This has London dispersion forces. This has London dispersion forces. This has a dipole-dipole intermolecular force. Butane doesn't. The boiling point for ammonia is minus 33.3 degrees Celsius. The boiling point for butane is minus 1 degree Celsius. Even though it doesn't have dipole-dipole interactions, because butane is so much bigger, it's got such a large electron cloud, relatively speaking, the London dispersion forces here are greater than the combined polar LDFs and dipole-dipole for ammonia. And there's actually a subset of dipole-dipole called dipole-induced dipole. An induced dipole occurs on a nonpolar entity. It's essentially a caused instantaneous dipole. The nearby polar molecule causes the electron cloud of the nonpolar entity to be not totally symmetric. The slight negative charge will push the electrons in the nonpolar entity to the other side of the molecule. And so this really is analogous to an instantaneous dipole. So you take a look at HBr again. Hydrogen slightly positive, bromine slightly negative. You put it next to an oxygen molecule. Now the oxygen molecule is nonpolar, there is no dipole. But the slight negative charge of the bromine slightly repels the electrons of the oxygen. So there is now an induced dipole there. And the left side of the oxygen has a slight positive charge, and the right side has a slight negative charge. And now there is the electrostatic attraction between the bromine and the oxygen. This is slightly stronger than just having LDFs, but it's not as strong as having a dipole-dipole. So for intermolecular forces, to review, IMFs are those attractive forces between molecules. The differences in IMFs can explain the differences in some physical properties, notably boiling point and melting point. IMFs are explained based upon polarity, size, and qualitatively by Coulomb's law. Basically, opposites attract. We will eventually discuss 4 types of IMF. We have the London dispersion forces, and all molecules have London dispersion forces. Dipole-dipole, and that can be broken down to straight dipole-dipole, and then dipole-induced dipole, hydrogen bonding, and ion dipole. The latter 2 will be discussed in the next video. On a per molecule basis, the dipole-dipole is greater than a dipole-induced dipole, which is greater than LDS. But a larger nonpolar molecule may have a larger intermolecular force than a smaller polar molecule due to the fact that the larger electron cloud can have enough force to be greater than the LDF and dipole forces. And that's the first 2 intermolecular forces. In the next video, we'll deal with hydrogen bonding, which is another subset of dipole-dipole, and then ion dipole.